Swayam Prabha. Digital India. Educated India.
I am Dr. Rajiv Mishra, working as professor in the Department of Computer Science and Engineering at Indian Institute of Technology, Patna. The title of this lecture is Time and Clock Synchronization in Cloud Data Centers. So, content of this lecture is as follows. We will discuss the fundamentals of clock synchronization in cloud and its different algorithms. So, this particular concept is valid for edge as well. We will discuss the causality and the general framework of the logical clock and present two systems of logical time, namely the Lamport and the vector time stamps, to capture the causality between the events of distributed computation. Again, let us summarize what we are going to discuss here in this lecture. So, in the edge and the cloud systems is primarily a distributed systems, and the time synchronization or a clock synchronization across multiple nodes is one of the important issues, and we are going to see the methods. There are two methods. One is called the physical clock synchronization, and the other one is called the logical clock synchronization. So, we are going to discuss these clock synchronization. Before that, we are going to see why this clock synchronization is needed in such systems, that is the edge and the cloud systems. Now, there is a need of why there is a need of clock synchronization. Let us see our example. In that example, let us say that we want to catch a bus at 9:05 a.m., but your watch is off by 15 minutes. What if the watch is late by 15 minutes? Then you will miss the bus. What if your watch is fast by 15 minutes? You will end up unfairly waiting for a longer time than you intended. Therefore, the clock synchronization is very much needed for the correctness and the fairness to ensure. In the first case, it is called the correctness, that means when you miss the bus, when you miss the event. For example, if you are late by 15 minutes in the class, so you will miss the class. Similarly, if you are ahead of 15 minutes for any event, that means you are ahead of 15 minutes, then you will be waiting for a longer duration of time that you intended, and this contributes to the fairness. So, in both the cases, neither your clock should be behind or late, nor it should be ahead, that is fast. So, this particular aspects, now we see that this particular thing is called the clock synchronization. If the clocks are synchronized, then you can ensure the correctness and ensure the fairness at all point of time in ordering the events or in detecting or catching the events. Now, time and synchronization. So, for example, if you have a clock or a watch which you are now seeing to synchronize with the standard time, then that is good enough. It will be synchronized at a particular point of time, but after some time again it will drift apart, and then you have to synchronize again and again. How about in a distributed systems? In a distributed system, it is not a one clock, but it is a series of systems, and every system is having its own clock. So, every system will have its own clock. Then how are you going to synchronize all the clocks, that is all n clocks, and that is called the distributed time. So, the notion of the time is well defined at each single location, but the relation between the time at different location is unclear. So, therefore, we have to ensure the time synchronization across all the systems to ensure the correctness and fairness, like in the previous example we have seen. So, therefore, there is a need of clock synchronization algorithms here when large number of systems, especially the distributed system, is in place, and that is called the distributed time. Let us see the techniques about that. Now, whether it is a cloud or an edge system, let us see the synchronization, how it is going to affect the applications. So, take for example, a cloud based airline, cloud and edge based airline reservation system. Now, here let us see that there are applications which are using this cloud edge system for airline reservation system, and here let us say server X replies a client request to purchase the last ticket on the flight. Here let us say PQR 123, and the server X timestamp the purchase using its local clock, that is 6 hours 25 minutes. Now, that was very last seat that server X sends the message to the server Y saying that the flight is full. So, this is server X and this is server Y. So, server X is sending server Y that the flight is full. Now, Y enters that flight PQR is full and its own local time was recorded as 6 hours 20 minutes, and when the flight was full, that was 6 hours 25 minutes. So, you can see there is a time difference. Now, server Z queries X and Y's log. Now, is confused that the client purchased a ticket at X after the flight became full at Y. So, you can see that at 6:25 it will get the information that at 6:25 the flight was full, it was the last ticket, whereas at 6:25 that flight was full. So, there is a clock synchronization time. So, the server Z will get confused that how come at 6:20 the server Y could see that the flight is full, while at 6:25 X could purchase a ticket, that is was the lost. So, this confuses the client if the clocks are not synchronized. So, therefore, this particular synchronization in the cloud and edge system is very much needed here to understand the transactions or the applications which are interacting for different purposes. Now, what are the key challenges here for the clock synchronization? Now, end host in the internet based systems like cloud have its own clocks, as I told you, unlike the processor CPU within one server or the bus station which share a system clock, and in the distributed system it is not possible to share the clocks in distributed systems such as the cloud, edge system, etc. So, it is not possible to share the clock, unlike you can see here in the server or the workstation. So, let us see about what are the challenges, how we are going to synchronize the clock in such internet based and hosts systems like cloud. So, the processes in the internet based system follow an asynchronous model. So, what is an asynchronous model? For example, if two systems which are communicating through the messages follows an asynchronous model in the distributed systems. So, asynchronous model says that the messages which are being communicated are having a delay. That means, when let us say a message is sent at a time t 1, it will be received at time t 2. So, there is a difference between t 2 minus t 1. So, this is called the message delay. The other delay is called the processing delay. So, once the message is reached, it will be now it will have incur some delay, and that is called the processing delay. Let us say that after t 3 the process completes its execution. So, that particular the other type of delay, that is called computation delay, is nothing but t 3 minus t 2, that is the delay due to the computation delay. So, there are two types of delays which is incurring, one is called message delay, the other is called process delay or processing delay, and these particular bounds are not known in an asynchronous model of computations. So, we are not talking about the single system which is called the server or the workstation, which is an example of the synchronous system. So, let us summarize what we have seen here in this slide is the model. The system model for clock synchronization that we are going to discuss considers an asynchronous model where the message delays are having no bounds. Similarly, the processing delay also is also having no bounds. So, such model is called asynchronous model. So, under this asynchronous model, we have to see the clock synchronization, how is it possible to be done. So, this becomes a key challenge. So, let us see some of the definitions before we go ahead in considering all the systems. So, asynchronous distributed system consists of a number of processes, and each process has a state, that is the value of the variable, and each process takes the action to change its state, which may be an instruction or a communication action, that is send or receive, or the actions. So, event is the occurrence of an action. So, a process has a large clock, and events within the process can be assigned the time stamps and thus ordered linearly, but in a distributed systems we need to know the time order of the events across different processes. Meaning to say that here we have, let us say that two processes, maybe that many processes will be there. This is process A and this is process B. So, each process has its values of the variables. Let us say variable is V 1 and V 2. So, the process takes this action to change its state, which may be the instruction or communication action. So, here for example, the state may be changed due to an instruction. So, if it is due to the instruction, that is called local event. The other is this is the one event number 1. The other type of event will be here the process 1 will send a message, this is called a send of an event, and the process B will receive a message. So, it will be a receive of an event. So, there are 3 types of events which we are going to consider. One is called internal process event due to the instructions which are executing in the system. The other is called send of a message is an event. Third one is called receive of a message is an event. So, there are 3 types of event we are considering in our definition, and each process has its own clock. Each process has its own clock, and all the events, that is called internal events, they are being time stamped with their local clocks, and thus all the events which are generated by through this particular instruction internally, they are all linearly ordered, that we have to assume. But in a distributed system, we need to know the time order of the events across different processes. So, if multiple processes are running different events, so how are we going to order them in a distributed system, that we are going to see in this particular discussion. So, for that, let us see a diagram which is called a space time diagram. A space time diagram will now order the events, try to order the events in the distributed system. So, here this particular mechanism is called space time diagram. Here the space means that the processes are independent entity. Here there is process number 1, process number 2 and process number 3. 3 different processes are separated and they are flowing their event, they are executing independently and the time is flowing. So, you can see that the time flows. Now, P1 will have the event at process 1, that is called E1, and internally another event happens in the same process, that is called E2, E3, E4, E5 and so on. So, they are all called internal events. So, we have seen the internal events of process P1. Similarly, for process 2, the internal events will be the event number 1, then event number 2, event number 3, event number 4 and event number 5 and 6. So, we have seen the internal events of process 2 also. Similarly, for process 3, the internal event is 1, then 2, 3, 4 and so on. So, we have seen the internal events of process P1, process P2 and process P3. Now, the next type of event which is called send of a message. So, here you can see the process P1, the event number 2 becomes the send of a message. Send of a message at this process 1 and send of a message in the process 1, that is event number 5 is the message send events. So, there are 2 message send event, they are in process 1, that is event number 2 and event number 5 are the message send events. Whereas, process 2 is concerned, event number 3 is a message send event and process 3 is concerned, event number 4 is a message send event. Whereas, receive event, if we see the process number 1 has event number 4 as a message receive event, process number 2 will have event number 5 as the message receive event and process number 3 has event number 2 as the message receive event. So, all the events are divided into 3 different classes, either they are internal events or a send of a message events or a receive of a message events. So, all the events are divided and they are represented here in a space time diagram which reflects the distributed execution in the space time diagram. Now, let us see there are 2 concepts in the clock synchronization. One is called the clock skew, the other is called clock drift. Now, each process running at some end host has its own clock that we have already seen and assumed. Now, when comparing two clocks at the two processes, so there is a concept which is called a clock skew. So, let us say that this is one clock and this is another clock. This particular clock is at A process and this is at B. Now, if you compare these two clocks at two processes, you have two different things to compare. One is called clock skew. So, clock skew is the relative difference in the clock values of two processes. Okay, relative difference means if this is showing as 12 o'clock, it is showing as, let us say, 2 o'clock, and here it is showing as 4 o'clock. So, that difference, this is called a clock skew, that is the relative difference in the clock values of the two processes. For example, the clock 1, clock at A is showing 2 p.m., whereas clock B is showing 4 p.m. So, this difference is called a clock skew. Now, another concept is called a clock drift, that is the relative difference in the clock frequency, the rate of the two processes. So, that is called a clock drift. So, clock drift says that the relative difference of the clock frequencies, that is the rate, relative difference in clock frequencies, that is called the rate. So, these two concepts are there in the clock synchronization. So, a non-zero clock skew implies that the clocks are not synchronized. A non-zero clock drift causes the skew to increase eventually, and therefore, if a faster vehicle is ahead, it will drift away, and if the faster vehicle is behind, it will catch up when the drift away. So, this indicates that both the measures have to be understood, that is clock skew and clock drift in the clock synchronization to last long if the clock is synchronized before it goes in asynchronous way of giving different clock values. Now, let us see what are the clock inaccuracies will be there. So, clock must not only be synchronized with each other, but also have to adhere to the physical time, and that is called the physical clock. Now, physical clocks are synchronized on an accurate real time standard called universal coordinated time. That means, if you want to synchronize your watch or a clock, then you have to now depend upon the accurate real time standard, that is universal coordinated time UTC, and from there you have to now synchronize your clocks, that is called physical clock synchronization. With the accurate real time standard called universal coordinated time. Now, however, due to the clock inaccuracies, a timer or the clock is said to be working within its specification if a constant rho is the maximum skew rate specified by the manufacturer. So, that is what is shown over here, that is the constant. So, here you can see that this is the perfect clock, where dc by dt the behavior of a fast slow, and the perfect clock with respect to the universal time clock. So, here you can see that if dc by dt is equal to 1, then it is called perfect clock. If dc by dt is more than 1, then it is called a fast clock. If dc by dt is less than 1, it is called a slow clock. Now, how often to synchronize, this is another important thing. So, the maximum drift rate MDR of a clock. So, absolute MDR is defined to be the relative coordinated universal time. So, universal time clock is the correct time at any point of time. So, maximum drift rate MDR of any process depends upon the environment. So, maximum drift rate MDR between two clocks with similar MDR is 2 times MDR. So, given a maximum acceptable skew m between any pair of the clocks, they need to synchronize at least once every m divided by 2 MDR time units, since the time is equal to distance upon speed. Now, let us go ahead about understanding about the clock synchronization. There are two types of clock synchronization, one is called external clock synchronization, the other is called internal clock synchronization. Now, to understand these concepts, consider a group of processes. In external synchronization, each process Ci's clock is within the bounded D of a well known clock S, that is an external to the group. So, here you have an external clock and then you have again the set of clocks. So, this particular synchronization of the clocks with the external clock called external synchronization, where each process's Ci's clock is bounded D of a well known clock S, that is external to the group. So, therefore, if this is Ci, so Ci minus S absolute is bounded by that particular D at all points of time. This is called external synchronization. So, external clock may be connected to the universal coordinated time or an atomic clock. The example of such mechanism that is called external synchronization are the two algorithms called Christian's algorithm and network time protocol or NTP. Now, we have another type of synchronization called internal synchronization. In internal synchronization, here the external clock will be the missing. So, in internal synchronization, every pair of processes in a group have a clock within the bound D. So, we are now going to consider in the internal synchronization only the clocks within the particular group, and in the internal synchronization every pair of processes, when you consider this pair of the processes in the group, have the clocks within the bound D. So, therefore, if it is I and this is j, then Ci minus Cj is absolute is bounded by D at all points of time for any two pair of processes here, and the algorithms which deals with the internal synchronization, they are called Berkeley's algorithm and data center time protocol. NTP is network time protocol. Now, therefore, what we see between external synchronization and internal synchronization, there is a bound. We say that external synchronization with the bound D is equivalent to the internal synchronization with the bound 2 times D. That is, the internal synchronization does not imply the external synchronization. In fact, the entire system may drift away from the external clock S. Now, let us see some of the basic fundamentals. So, external time synchronization, here all the process P synchronized with the time server S. So, here we can see that the process P wants to synchronize its clock with the external time server, let us say S. So, here let us say the P sends what is the time, this particular question to S, and S will say here is my time at time t, and it will set the time at to t by P. So, let us see what is the wrong in this, what is the problem in this kind of clock synchronization. So, by the time the message has received at P, here there will be a delay. that is called the message delay. So, by the time the message has reached at p, the time has moved on. So, the time when it has received the message, the correct time was not t, but let us say t prime. So, p time set to t is inaccurate, it should be t prime. So, this inaccuracy a function of message latency. Since the latencies are unbounded in the asynchronous system, the inaccuracies cannot be bounded. So, this particular message delay is often unbounded, because we have considered an asynchronous model, which is stated in the previous slides. Let us see the Christian's algorithm, which is the external synchronization algorithm. So, it has an external clock and a process P who want to synchronize its clock using Christian's algorithm. So, P measures the round trip time of a message exchange. Suppose we know that the minimum P to S latency is minimum 1, and the minimum S to P latency, let us say min 2. So, min 1 and min 2 depend upon the operating system overhead buffers to buffer the messages and TCP time to queue the messages, etc. Why? Because this particular communication or messages now has to deal with the buffers and the TCP time to queue the messages. So, the actual time at P when it receives the response is between t plus min 2 here to t plus RTT, t plus RTT minus min 1. So, this is the actual time at P when it receives the response is between t plus min 2 and t plus RTT minus min 1. So, meaning to say from here you can see that from here you can see that this is when you say t plus RTT, t plus RTT minus min 1. So, this is the delay, and t plus min 2, that means if you know t time t plus min 2, if this is the t time t plus min 2, or it is t plus RTT minus min 1. So, this is the actual time at P when it receives the responses between this particular range. So, let us see about the Christian's algorithm. So, the actual time at P it receives the response is between t plus min 2 to t plus RTT minus min 1. So, P sets its time to the halfway through this particular interval, that is t plus RTT plus min 2 minus min 1 divided by 2, that is error is at the most RTT minus min 2 minus min 1, and this is bounded. So, let us see once more about this error bounds in Christian's algorithm. So, if let us say that this is the time server and this is the client which wants to synchronize the time as per the server. So, it sends a request at let us say time t 0, and this particular request is being served by the server, and the server will send the time t here in a reply message. So, this will be received at time t 1 at the client. So, let us see how the client will synchronize its clock in this particular manner. So, let us say that T0 when the message is received, let us assume that this particular message delay bound is T min, and let us say that on the other side receiving the message from the server again is bounded again by the same amount. So, the earliest times when the messages are received, here we can calculate that the range will be that T 1, this T 1 minus T 0 minus 2 times T min. So, this T min is same minus 2 T min is, that is the range. So, the accuracy of the result is, what we can find out is T 1 minus T 0 divided by 2 minus T min 1 T min. So, the error bounds what we have seen is they are allowed to increase the clock values, but should never decrease the clock value, may violate the ordering of the event within the same process. So, therefore, these they are allowed, clock synchronize, they are allowed to increase or decrease the speed of the clock. Why? Because the values cannot be decreased. So, the speed matters, which you have the control for it. If the error is too high, then take the multiple readings and average it. Now, let us see the Christian's algorithm through a running example. So, let us say that request is sent at time, let us say 5:08, and then response is received, that is T 1 at time 5:08 15,900, and it was at 100. So, the response contains the T server timing, and let us see that this timing is 300. So, the elapsed time is T 1 minus T 0, that is 900 minus 100 is 100 milliseconds, but the guess was guaranteed 400 milliseconds ago. Then it will set the time to T server plus elapsed time, that is the time of a T server is 300 and elapsed time, let us say 400, it becomes 700 time, and therefore, this particular time which is set by T 1 is 700. So, here if you can see the error is bounded with plus minus 200. So, in the best case the message will have 200 milliseconds of bound, and here all these things are explained here in Christian's algorithm. Now, let us see the next protocol, that is called network time protocol NTP, that is also based on the external synchronization, and this is the internet standard. So, internet uses this particular protocol called network time protocol. Network time protocol is organized in the form of network time protocol servers, which are organized in the form of a tree, where at the root there will be a primary server, and then there will be a secondary time servers, and then tertiary time servers, and then comes the client. So, network time protocol servers are organized in a particular tree. So, each client which is at the leaf of a tree, and each node synchronizes its clock with its parent. For example, this clock will synchronize its clock with the tertiary server, which is a parent of that clock client. So, network time protocol we can understand here in this case. So, this is at the child, and it want to synchronize its clock with the parent. Now, the child will send a message, let us start the protocol, and the message 1 send time is, let us say T s 1. It will send a message, parent will send a message with the time T s 1, and this particular message will be received by child at T r 1. T r 1 is according to the clock value of that child, and parent 1 T s 1 is the clock value of its parent clock. So, this child will synchronize its clock with the parent clock here using network time protocol. So, it sends its clock value, that is called T r 1, it time stamps at TR1 when it receives it, it sends it as TS1. Now, then child will send again another message, that is message 2 at TS2, send the time, that is TS2, that is and it will be received, and it will send the message received time, that is TR2, it will send it back with TS1 embedded within it. So, after this exchange of messages, all these times will be received by the client TR1, TR2, TS2, TS1. By this we are going to calculate an offset small o, that is TR1 minus TR2 plus TS2 minus TS1, and we call it as offset. And using this offset, let us calculate the error. Suppose the real offset is O real and the child is ahead of a parent by O real, parent is ahead by a child minus O real. Suppose one way latency of a message 1 is L1 and no one knows about L1 or L2, then we are going to calculate TR1 and TR2 using these two equations, and then using these two equations we are going to solve, and we will obtain O real, and this particular factor becomes offset that we have already seen. So, offset O real is offset plus L2 minus L1 divided by 2. So, O real minus offset is less than L2 minus L1 divided by 2, which is, let us say, bounded by L2 plus L1 divided by 2, and thus the error is bounded by the round trip time. This is nothing but the round trip time in this particular case. Now, we are going to see another algorithm, that is called Berkeley's algorithm. So, Berkeley's algorithm, as we have seen, that this is the internal synchronization. So, here in this case, this Berkeley algorithm was given in 1989 by Gusla and Jetty, where the masters poll each machine periodically, ask each machine for the time, can use for this the Christian's time to compensate the network latency, and when the result are in compute including the master time, and here the average cancels out individual clock's tendency to run slow or fast. So, let us see about the Berkeley's algorithm. Here the request timestamp from all the slaves is sent in the step number 1. So, each timestamp, each slave or each client will send its clock values to the central coordinator, and then coordinator, what it will do, it will see the clock values and find an outlier. So, it will remove the outlier and then take the average including that particular clock value, and let us say that it is that average is 305, and then this average of this particular current offset will be now sent for this offset to each of these particular clients. Now, we will see the data center time protocol. Data center time protocol is also the internal synchronization, it is a globally synchronized time via the data center networks. So, data center time protocol uses the physical layer of the network devices to implement the decentralized clock synchronization protocol. It is highly scalable with a bounded precision, and it assumes that how many hops your data center is away, and what is that particular latency between that, and between the peers also it considers that bounded precision. Here we assume that there is no network traffic and internal clock synchronization is only possible here, end to end precision is of the order 200 nanoseconds. So, here you can see that in data center time protocol it runs in 2 phases between the peers, initialized phase measuring the OWD and beacon phase used to resynchronize So, this is the initialization phase that we have already seen the delay computation, and then it will be having a beacon phase, and then it will consider about the data center time protocol switches also into a consideration, and then it will be considering the DTP property, which is bounded precision and scalability. And we can see that all these methods have a non-zero error even after the synchronization of a clock synchronization is done. Now, the question is, how do we get rid of these particular errors? Even of the clock synchronization algorithm also is not eliminating the error to 0, it is always non-zero, because the messages are having the message latency and these latencies are non-zero. So, how can we avoid this synchronizing the physical clocks? So, how to avoid physical clock synchronization? And still we can order the events. So, what is the use of this clock synchronize? To order the event in the distributed systems. Now, how to avoid the physical clock synchronization, yet we can order the event in a distributed system? That is the question. So, let us see the method of ordering the events without physical clock synchronization in a distributed system. Let us see in a distributed system how to order the event without having the physical clocks. So, in order to order the events across the processes which are trying to synchronize the clock is one of the approaches, but what if the assigned times of to the events are not absolute time? Then as long as those times obey causality, that would work. What do you mean by causality? Causality says that if an event A causally happens before another event B, then the time stamp of that event A should always be less than time stamp of event B. So, as far as the humans use causality at all points of time, for example, I enter the home, only I unlock it. So, unlocking means opening the lock and then entering into the home. So, the entering into the home, unlocking happens first. So, the time stamp of unlocking happens is less than the time stamp of entering into the home. So, this is called causality. Humans are very good at it at all points of time. Similarly, another example is that you receive a letter only after I send it. So, send of an event of a letter having the time stamp less compared to you receive the letter at later point of time. So, this particular relationship in ordering of the event is called causality. Causality may not require the physical clocks in a distributed system, that is what we are going to see. If the physical clocks are avoided, yet we can order the event with the help of a relation which is called causality, that we are going to see in a distributed system perspective. This concept was given as logical ordering, and this is given by a famous scientist which is called Leslie Lamport, and that is why it is called Lamport's ordering. So, this particular idea was proposed by Leslie Lamport in 1970s and is being used in all the distributed systems since then. When you say all the distributed systems, whether we design an edge computing system or a cloud computing system, all of them they require this logical ordering of events, and this is one of the most fundamental concepts in building up the cloud computing systems or the edge computing system. So, all of them, that is cloud and the edge, will use some form of logical ordering of the event. Now, there is a brief biography of Leslie Lamport, who got the highest award in computer science, that is called Turing Award, 2013 Turing Award. Leslie Lamport was the winner of Turing Award for imposing clear, well defined, seemingly chaotic behavior of a distributed system in which several autonomous communicate with each other by ordering the messages, and his particular work of logical ordering was recognized as the best work. Leslie Lamport's, if we go to highlight some of the important contributions. So, it laid through these kind of fundamental theories, it laid the foundation of distributed system, and therefore, this particular distributed system principles are used in building the cloud computing, edge computing. His paper, which got him recognition of this award, is called Time, Clock and Ordering of the Events in a Distributed System, and which got the best paper award. There are many other works which are very much required here: a part-time parliament, distributed snapshots, Byzantine journal problem. Some of them we are going to cover in the design of edge computing systems. So, these papers relate to the concepts such as logical clocks, and that particular logical clock is dependent upon a particular relation, that is called happened before relation, in Byzantine failures, and they are the most cited paper in the computer science and describe the algorithm to solve many fundamental problems in distributed system. Notably, his work is about designing the Paxos algorithm for consensus. In all the internet based applications which are running, they use this Paxos algorithm. Berkeley algorithm for mutual exclusion, Chandy-Lamport algorithm for determining global state snapshot, and so on. So, all these are seminal works of Leslie Lamport. So, we have just remembered it in his honor, that whatever we are studying, that is in the edge computing, cloud computing, all have the contributions, fundamental contributions of a distributed system developed by Leslie Lamport. So, the logical ordering, let us understand it. Let us define a logical relation, that is called happened before relation, among the pair of events, that is called happened before relation, which is noted by this particular symbol, and this is the relation called happened before relation. Now, this particular relation follows three different rules. The first says that on the same process A related to B with the happened before relation, if the time stamp of A is less than time stamp of B using the logical clock. If P process is an event which sends a message to P1, then send off the message has happened before the receive of a message. Similarly, the transitivity says that here also you can see that send off event has happened before. Now, transitivity says that if A has happened before B and B has happened before C, then A has happened before C. So, this particular three different rules will create the partial order among the events. So, by this way you can create the partial order. In distributed system. This means that not all events are related via this happened before relation. So, we are going to see about the Lamport's ordering. This is also called the logical ordering. Of clocks in distributed system. when we say distributed system, that means this logical ordering of the clocks is as well used in the cloud and in the edge computing systems. So, let us define this relation, which is called a happened before relation. So, happened before relation among any pair of the events is denoted by this particular symbol. So, this is called happens before relation. Let us define a happens before relation, and this is represented by this particular symbol. Now, this particular happens before relation follows three different rules. The first rule says that on the same process, that is for the internal events, when you say internal events means within a process all the events which are happening. So, within that particular event, if there are two processes which are related causally with the happened before relation A happened before B, this implies that if the time of A, event A is less than time of event B. The second type of event is called send of a message event. So, if P1 sends a message to P2, so the send of event happens before the receive of that particular message. And third rule follows the transitivity property. Transitivity property says that if A has happened before B and B has happened before C, this implies that A has happened before C. So, these three rules are defined as the logical or a Lampert's ordering. Now, these particular three rules, if you define between any set of any pair of events in a distributed system, then it is going to create a partial ordering of events. In distributed system. So, therefore, when you say partial ordering of events in a distributed system, that means not all events are related here in this case. So, that means we need a total ordering, that means some additional rules we have to add to achieve the total ordering of events in distributed system. So, up to this point we have achieved the partial ordering of events in the distributed system with the help of logical ordering, that is called Lampert ordering. Let us understand this through a diagram or example. So, in this example we are showing this time space diagram. In this time space diagram, we are considering three processes, that is P1, P2 and P3, and let us see that the P1 has the internal events A, B, C, D, E. Out of them A, B, A, C and E, they are internal events. A and C are internal events, whereas all other events are, for example, it is a send of a message event. This is again D is also receive of a message event, and E is also send of a message event. Whereas in process P2, E is the receive of a message event, and F is also a receive of a message event, G is a send of a message event, and you can see in a process P3, H is the send of a message event and I is an internal event and J is the receive of a message event. So, here let us see about the message exchange, and let us see that A has happened before. Here in this case, as per the rule 1 is concerned, A has happened before B using rule 1 of logical ordering, B has happened before F, that is rule 2, and therefore, this implies that A has happened before F using rule 3. Now, consider furthermore, F has happened before G, this is the internal, this is the rule 1, and G has happened before D, this is according to the rule 2. Therefore, this implies that F has happened before D. Since A has happened before F and F has happened before D, this means this also implies that A has happened before F using rule 3. A has happened before F. Now, further F has happened before G and G has happened before D. So, F has happened before D. So, if you consider this will imply that A has happened before D again by rule 3. And similarly, D has happened before E. So, this will imply that A has happened before E, and this proves that this is happening internally into the system, whereas H has happened before E and E has happened before F and F has happened before G and G has happened before D and D has happened before E. So, H has happened before E here in this case by transitivity rule 3. Now, what we see here is that although many of these relations, many of these events are ordered, but not all the events are ordered using causal order. For example, if you want to find out what is the relation between E and C, so there is no happened before relation between E and C, and such relations are called concurrent events. So, they are called concurrent events, do not have the happened before relation. Therefore, the ordering which is given by this partial ordering is a partial order, this by the logical clock is a partial ordering. So, this is the example which we have already covered. A has happened before B and B has happened before F. So, A has happened before F, and here also these relations we have explained. Now, using Lampert's time stamp, the goal is to assign the logical or a Lampert time stamp to each events. As we know that these time stamp obey causality, the rule says that each process uses a local counter, that is the clock with an integer value, and initialize this counter to 0. So, a process increments its counter when a send or an instruction happens at it. So, the counter is assigned to the event as its time stamp. So, send of an event carries a time stamp, receive of a message event, the counter is updated by the following formula, that is the maximum of the local time and the message timestamp plus 1. This is how the clock is updated when a message receive event has happened. Let us see this through an example. So, initialize all the clock values of all the processes counters to 0. So, let us see that the clock of process P 1 will have the first event, that is internal event, will increment the clock, increment the counter as 1. So, this will have the timestamp 1. Similarly, as far as process 3 is concerned, the event which is called send of a message event will have the timestamp as 1 here in this case. Now, let us see that when this particular message, that is called send of a message, will have, when the message will be carries this T S 1, and when it receives over here the receive of a message now will update the clock of P S 2 in the following manner. So, it will have its local time and the time which the message has come, maximum of these two time. So, the local time of P 2 is 0, whereas the message T S 1, that is timestamp 1, will be covered in the message. So, 0 and 1, the maximum of 0 and 1 will become 1 plus 1. So, this particular time clock after the receipt of this message will be updated as 2, and so here you can see that we have seen that this is updated as 2. So, this is internal clock, and the next event which is message send event will carry this timestamp 2, and when this particular message will be received over here. So, the maximum of the internal time and the message which it carries plus 1 will be the time which is updated. So, internal time is 2 and the message which also carries is 2. So, maximum of 2 plus 2 and 2 is 2 plus 1, that becomes 3. So, 3 will be the time which is set here in P S 2 when the message is received. So, this we have already seen. Now, coming to this particular event, receive of a message, we receive of a message at this particular time here at P 1. Now, it will be the internal event is 3 and the message which carries the timestamp is, let us say 4. So, maximum of 3 and 4 is 4 plus 1, that is 5. So, it will set the time as 5 here in this particular case. Similarly, this time will become 6 and finally, the 7 time will be updated in this case. So, internal is 2, the message which it carries is 6. So, the maximum of 2 and 6 is, let us say 6, and thus plus 1 will be there. So, it will be the 7 here in this case. So, let us see that what are we going to conclude here by obeying the causality. So, if A is happened before B, that means that the clock value of A is less than the clock value of B. So, that is satisfied. When B is happened before F, so this means that the clock value of B, which is 2, is less than 3, that is also obeyed, that is it is obeying the causality. A and F, when we talk about these two scenarios, so the clock value of A is 1 is less than 3. So, therefore, they are obeying the causality relationship. Here also we can see that all the relations are being obeyed here in causality. Now, the question is, not all the events are ordered. So, that is why it is called a partial order. Let us find out those events who are not being connected with the happened before relation or not following the causality. If we see C and F, now C and F, they are not happened before relation, they are not related with the happened before relation. Although their values are same, but we cannot infer anything Why? Because C and F they are not related, therefore, their clock values has no meaning. Similarly, H and C, you see the H and C they are not causally related, therefore, their clock values even if H is less than the clock value of 3 does not have any significance and they are not obeying causality. Therefore, we cannot see their clock values and can infer anything about that. Now, C F and H and C pairs which are not related causally, they are called concurrent events. So, concurrent event means a pair of concurrent event does not have a causal path from one event to another, either way in a pair. So, Lampert's time stamp not guaranteed to be ordered or unequal for concurrent events. So, the concurrent event, how we are going to handle this concurrent event which is not covered here anything in the causal ordering or that is in the Lampert clock or a logical time. Therefore, concurrent event are not causally related. Remember that if E1 happened before E2, this means that time stamp of E1 is less than time stamp of 2. But if you directly look into the time stamp of E1 is less than time stamp of 2, this has two different meaning. That means, either E1 has happened before E2 or E1 and E2 are concurrent event. So, here by looking the time stamp, if E1 has happened before E2, this we infer here. So, by looking up the time stamp, we cannot infer whether they are causally related or not related. So, this is called, this is the drawback of logical clocks, that by inferring the time stamp or by seeing the time stamp, we will not be able to infer anything about that. Now, because of the partial ordering, it only considers the partial ordering of the event. How about the other type of strong logical clock? So, the other clock is called the vector clock, and that is called the vector time stamp. Now, let us see that this vector time stamp is used in the internet based key value store, that is the database like REAC and all these things are using the vector time stamp for ordering of all the events. So, events means the transactions. So, each process, let us understand about this important concept, this is called vector time stamp, which is heavily used in most of the practical systems. So, vector time stamp here, let us consider that each process uses a vector of integer clocks. What is this? Suppose that there are n processes in a group 1 to n. So, each vector will be having n elements. So, each process I will maintain a vector v 1, v I, a process I maintains a vector of n dimension, that is 1 to n. So, jth element of the vector clock at a process I will be represented in this particular manner, that is for a process ith, jth clock, that means jth clock's value which process I has the knowledge, means that I is knowledge of the latest event at process j. So, this is called the vector time stamps. Now, let us see the rules of vector clocks. So, how to increment the vector clocks? So, it has three different rules. The first rule is said that on an instruction or send of event at a process I, it increments only the ith element of its vector clock. The other type of event, the other type of increment says that each message carries a send events vector time stamp, that is this vector of that particular message will contain into the send of event. On a receive of an event at process I, it follows two steps. The first one is that it increments its clock values, that is at the ith process, at ith vector it will increment, then it will update all other vectors except I. That is done using the max function. What it says that all the vector times which comes along with the message and the local knowledge of process I about that vector j, except I, maximum of them will be updated here in the clock. So, this will be an update in the vector clock. So, let us see through an example. Here we have in a vector clock we have 3 different processes P 1, P 2 and P 3. So, therefore, their vector clocks will be initialized, with 0 0 0 all of them, and then you know that as it increments its values, these particular values are being updated. This is the internal events. So, internal clock will be updated, and when the events are changing, so it will update its local clock here in this particular manner. So, let us understand how this receive event is updated. So, when a receive is updated in the following manner. So, for example, when a message with 0 0 1 is received. So, once the message is received, so first of all it will increment its own local time, and then it will update 0 is not updated and 1 will be updated, 0 will be updated to 1 here in this case. So, therefore, we have seen about the vector time stamp and different other conditions we have seen so far. Now, what we see, the vector time stamp follows causally related. That means, if we see the vector time, then there are 3 different relations. If vector time t 1 is less than or equal to vector time t 2, this means that vector time t 1 is less than or equal to t 2 for all values of n. 2 events are causally related if and only if vector time t 1 is strictly less than vector time t 2. Not causally related, that means, if 2 events are concurrent, that means, if neither V t 1 is less than V t 2, not V t 2 is less than V t 2. Therefore, this is called concurrent event here in case of vector time stamp. So, vector clocks obey the causality, and which is shown over here with all different examples. In this example, you can see that C and F by even by the comparing their vector clocks. So, here it is higher, but it is lower, but here it is lower and this is higher. So, therefore, neither it is the clock value of C and F, neither C is less than F nor F is less than C. So, they are concurrent event, that is shown over here. So, just by looking the clock values, you can infer whether they are concurrent event or happened before relations. So, let us summarize the logical time stamps. So, we have seen 2 different time stamps, one is called Lampert's time stamp, the other is called vector time stamp, and Lampert time stamp are the integer clocks assigned to the event obey causality, but cannot distinguish between the concurrent events. Vector clocks obey causality, and by using more space it can identify the concurrent events. So, conclusion is that clocks are unsynchronized and asynchronous distributed system, but need to order the event across the processes. We have seen 3 different clock synchronization method: Christian's algorithm, Berkeley's algorithm, network time protocol, data center protocol, and also we have seen the method to avoid the time synchronizer altogether by instead assigning the logical time stamp to the events. So, with this, let us conclude this particular lecture. Thank you.